Last couple of classes, we extensively discussed about the analysis of proton spectra and the analysis of the spectra of several heteronuclei. Heteronuclei, what I mean is anything apart from proton like carbon, fluorine, phosphorus, nitrogen 15, boron, selenium, silicon, platinum, varieties of nuclei we covered. And especially we took deeper into carbon 13 NMR, where I showed which is a common nuclei apart from after phosphorus, that is most extensively studied nuclei. Lot of examples we did. And I showed you how we can even get the chemical shifts. We can calculate the chemical shift on phenyl rings, carbons, chemical shift of the carbons, especially the phenyl groups are there based on the substituents. And depending upon which carbon you are looking at it, whether it is ortho to the substituent, para or meta, and which is the substituent, whether it is mono or di, like that, asymmetric or asymmetric. So many examples we took. And also we analyzed carbon 13 and we showed carbon 13 can be utilized to get the structure of the molecules. And I also said something about depth, distortionless enhancement, polarization transfer. Using that we can edit the carbon spectra, in the sense identify the carbons where it is attached to different types of protons. We can identify CH3 carbon, CH2 carbon, CH carbon, quaternary carbons. And in the phosphorus, fluorine NMR, many examples we took where we could analyze very easily. And these are all friendly nuclei, spin-off nuclei. We could get the coupling between themselves, homonuclear coupling of fluorine or homonuclear coupling of phosphorus, or heteronuclear coupling between phosphorus, fluorine, abundant spins and dilute spins. And many examples of spin half nucleus, spin one, more than spin half, like, and how they are coupled with spin one, what is the type of pattern we get. And when you are looking at spin, quadrupolar nuclei coupled to spin half, or how this pattern you are going to get, like N14 of nitrogen 15, or boron spectrum of BH4 plus minus NH4 at ion. Many examples we took. And we got fairly confidence about the analysis of the spectra of different nuclei. You have got it. Okay. With this, we will switch over to a different topic, because so far I gave some concepts and analysis. Now I will give you one or two more concepts which is very important, so that we can afterwards we can jump into 2D NMR. For understanding 2D NMR, especially this, you need to understand what is called a J modulation, spin echoes, and also little bit about polarization transfer. So in the next one or two classes we will cover this thing, and then subsequently we will switch over to 2-dimensional NMR, where we can give some concepts and then analysis of the 2-dimensional NMR spectra. Okay, today I will start with spin echoes. Spin echo, you please remember, it is a basic pulse sequence, fundamental pulse sequence in NMR. Very fast, immediately after the discovery of NMR in 1945, within 5 years, Erwin Hahn introduced spin echo. Fantastic idea. This is one of the basic sequence, and it transformed NMR understanding a lot. So spin echo sequence is very important. It is used in many NMR techniques. We will come to that later how we do. What is the meaning of a spin echo? If you have a single RF pulse, that is what you have been doing. Apply RF pulse, tilt the magnetization, thermal magnetization to XY plane, and start collecting the signal. In the XY plane, the spin vector start dephasing, and then when it dephases, there is a decay of the signal in the XY plane while growing simultaneously along Z axis. That is what I said in the introduction class. While decaying the signal in the time domain, you collect the signal, do the Fourier transformation, you get the spectrum. The decay in the time domain, we call it as FID, which exponentially decays. That is all we discussed. This is when you apply a single pulse. What happens if you apply two successive RF pulses with some time delay between them? Not immediately, successively with a time delay. What will happen? Then we get what is called spin echoes. What are the spin echoes? We will try to understand now. Usually, a standard spin echo has a 2-pulse sequence, 90, tau, 180, tau. This is the sequence. 90-degree pulse, a delay, apply 180 pulse, a delay, and then start collecting the signal. This is a standard spin echo sequence. How it works, we will understand the concept later. But here, immediately after the 180 pulse, what happens is, after 90 pulses, the signal start dephasing. When it comes to magnetization, comes to XY plane, here they start dephasing. After some time, You apply a 180 pulse and give some delay, equal delay. This and this should be equal. And start collecting the signal. Then what is going to happen is, the 180, after 180 pulse and after certain delay, the spin vectors which underwent defacing in the first period will start refacing after this delay. Something, it is like a time reversal. You are reversing what is happening in the phenomena. What happens here? The spins which defaced, now we reface it after applying a 180 pulse and gives exactly equal amount of time. This is called echo time. From this to this is called echo time, refacing time. Okay. And echo amplitude decays with some time. Of course, I will see that later. How it works is like this. First 90-degree pulse tips the nuclear spin into transverse plane. That's what we have been doing. That is the basic thing of NMR. First pulse always brings the magnetization to XY plane, transverse plane. And spin isochromotes start moving faster and slower because they are defacing. Let us say from the x-axis, this is let us say my on resonance, and some will go, those which are on resonance will nothing will happen. Those who are here and here with a different offsets, chemical sheet offsets, these things will start processing. Some will go like this, some will go like this. This is called fast moving and slow moving components. Some of the spin isochromates move faster and some move slower. Those who move faster gain phase faster. Those who move slower will lose phase slower. Okay. Essentially, the spin isochromates start defacing with time. With time, entirely all the spin isochromates in the XY plane start completely defacing. That's the important thing. Apply 90 pulse, wait for some time, the spin start defacing. That's what we know. Now you apply a 180 pulse. What does 180 pulse does? It turns the entire spin system and reverses the phases of the isochromates. Very interesting. What is happening is, the faster ones start moving slowly and the slower ones start moving faster. Initially, when we have isochromates here, some are moving faster, some are moving slow. After 180 pulse, they all get interchanged here and they start moving in the, one which was here start moving slowly, one which is faster start moving slowly. So faster will start moving slowly and the slow one start moving faster. At exactly identical delay, that's what I said. First delay T and the second delay T, when it becomes equal, all the spin isochromates regain the phase coherence and we get AFID, which this is what is called echo. It is like telling there are several spin vectors here. Think of a situation. What will happen? Think of a running race. There are different people are standing here. What will happen? You ask all of them to start moving. Everybody start running. Different people will run at different speeds. That's fine. After some time what happens? Stop, allow them to stop wherever they are. See what would have happened? One fast runner would have moved faster, another one would have moved here, some would have moved slow, some would not have moved, some would have moved very little, like that, depending upon their speed. They are all at different places. Ask them to stop. Immediately whistle and ask them to turn back, reverse. Exactly like applying a 180 pulse. Ask them to turn back. Ask them to continue running back with the same speed. Because their speed will be identical and this fellow moved this much for time t, and after time t when he is asked to come back, same time t, he will come back here. He will also come back here. He will come back here. He will come back here. All the spin vectors, we started from a particular place, will come back to the same place. This is what is called an echo. What happens? It is like applying a 180 pulse. It is like different people who are running, going through a running race, have different speeds. After a time t, ask them to stop, take a reverse turn and come back to the same place, move with the same speed. then everybody will come back to the same place. This is all called an echo. Identical. So this is called spin echo. The coherence isochromats will gain coherence again. And this is what is called a term called echo. Echo means you will dephase for some time. After exactly a particular time t, apply a 180 pulse and exactly equal amount of time, the spin isochromats come back and rephase. Dephase isochromats will rephase it after the identical time with a 180 pulse in between. This is called an echo. Please understand this. This is the pictorially you can see this. First apply a 180 pulse, FID start decaying like this. Apply 180 pulse here. Then what is going to happen? Then they will, like as runners have reversed their phases, reverse their direction, they will again start going back like here. Whatever they decade, they start going. At the top of this, it is a echo. But in between this intensity and this intensity, slightly there is less. Because between this time, there is what is called a relaxation. If there is no, because of the relaxation, intensity of the echo has come down, but it forms an echo. It gets rephased. And this, of course, one of the T2 experiment, and we do this thing. We measure this decay and measure the dephasing time, that is T2, relaxation in the transverse plane, relaxation time. Okay, this is how spin echo works. This is a pictorial representation of a spin echo. Apply 90 pulse, wait for some time, spin start dephasing, apply 180 pulse, wait for the equal amount of time, the spin starts gaining phase and forms an echo here. That is important. So this is what is happening. What is happening? After the, to be precise, after the 90 pulse, the spin starts losing phase coherence. Coherence means signal magnetization in the XY plane. Okay. And then FID is not lost. After some time, things would have dephased. And it is a common assumption, we have lost the FID. No, FID is not lost, but the only phase coherence is lost. There is a decoherence, phase is lost, but FID is not lost. And the system will have some sort of a memory. It is a hidden memory is there. It is called atomic memory. It is there. Spins will have some atomic memory. And the second pulse rephase the dephase spin isochromats. This is what happens. So dephasing means not that FID is completely lost. It is system will somehow retain its memory, and that is regained by applying another pulse and then waiting for a time t. We are going to get the rephasing. What should be the flip angle for the second pulse? Of course, I said in the first example 90t, 180t. That is a common spin echo sequence. That's what I showed. Common spin echo sequence is first 90, t delay, 180, t delay, and collect the signal after echo. But should it be always 180? Need not be. It can be any angle. In fact, when Erwin Hahn, 1950, did the first spin echo experiment, it was 90t90 experiment. That's also possible. Any two pulses I said with a delay. I did not say 180 in the beginning. I showed it a commonly employed pulse sequence is for spin echo is 90t 180. And when the spin angles other than 90 and 180 are used, we call this as Hahn echo. Commonly, spin echo sequence uses 90t 180 t. If other than any of these angles is used, still you can get an echo, but it is called Hahn echo because we are honoring the scientist who gave this idea. That is called Hahn echo. Now we will understand what happens to chemical shifts, what happens to coupling, both in homonuclear case and heteronuclear case during spin echo sequence. And we will take the example of first two spins with different chemical shifts. I am not talking about the coupling at the moment. We will come to the coupling evolution later. Right now I am assuming only two spins, independent spins, different chemical shifts. And I am not worried about coupling, there is no coupling. Okay. I will take this example. Let us see for these two spins with the different chemical shifts, what happens in the spin echo sequence. We have two spin isochromats, one A, other is X. I told you spin, they have different chemical shifts. Apply a 90 degree pulse, bring both the spins to x-axis or y-axis in the xy plane. I'll always consider A spin on resonance. On resonance means it is when it's brought to x-axis, it is not moving, it's stuck there. Okay, it's not moving, there is no offset. It is on resonance. A spin will be always on x-axis. I brought to x-axis, it will be on x-axis. If you bring it to y-axis, on resonance, it will be always on y-axis. So because it's on resonance, A is not moving. What about x? X is not on resonance. So what happens with the time delay delta? X starts moving. Look, A is on resonance, not moving. X is moving. Whether faster or slower, I don't care, because some chemical shift difference is there, it is moving. Okay, it is a fast moving component we have taken. If it was this side, it was a slow moving. Fine. At this stage, what I will do is I am going to apply 180 pulse. What does 180 pulse does? It reverses. Okay, it completely turns the table like this. So what will happen? The vector which was here, I am applying 180 on the x-axis. It rotates along this x-axis. The rotation axis x along this axis, it completely rotates by 180 degree. Then what is going to happen? When it rotates by 180 degree, the vector which was here move to this side because I have rotated. Now what will happen? It starts moving. Faster became slow now because it is on the other side. It start moving slow. It became a slow moving vector, and it start moving like that. Wait for some time, a same delta time. Then what happened? After exactly equal amount of time, it will come to the same x-axis. Understand the point. X is not on resonance. With a time delay, x has moved somehow. Now you reverse it by applying a 180 pulse. They continue to move in the same direction now. And then after certain delay, it will again come back to the same x-axis. Like I gave the example of spin echo, where the runners go and come back at the same time after a particular period. Exactly like that, there is an echo. They come back. Spin vector comes back and it comes here. What happened over the time now? A has not moved because on resonance, forget it. But there was a chemical shift difference between A and X. As a consequence, A was moving. There was offset. Chemical shift offset was there. That's why A was moving. Fast or slow doesn't matter. But this 180 pulse, after delay, what we did is that after 2 delay, the phase difference between A and X is reduced to 0. They have 2 different chemical shifts. In spite of it, they come out of the same place. Now it appears as if there is no phase difference at all. That means there is no chemical shift difference between A and X. You can imagine a situation now. There were 2 chemical shifts between A and X. After spin echo, it appears as if they have the same chemical shift. There is no chemical shift difference. And this means I would say spin echo has refocused the chemical shifts. It is called chemical shift refocusing. I took the example of 2 homonuclear spins A and X. When you take homonuclear spins A and X, I showed that when the 2 spins are there, with spin echo, there is a chemical shift refocusing. There is difference in the chemical shift between them is removed. When the difference in the chemical shifts are removed, we call it as chemical shift refocusing. Alright, we will go. I took the simple example of 2 protons. Okay. You may ask me a question. In a given sample, it need not be always 2 protons. There could be many spins, many protons with different chemical shifts. Then what will happen? Of course, true. There is no difference at all. As soon as you bring all the spin systems into x-axis, there is coherence here. Along this axis is called magnetization. Apply 90 pulse, bring it to x-axis. Instantaneously, there is a phase coherence. At a given instant of time, as soon as you bring it to x-axis, there is a phase coherence. Now, with time, there is a decoherence. Some are fast moving vector, some are slow moving vector, they start moving. Some move this side, some move this side with respect to this one, x axis. Continue for a longer time, they keep on defacing like this. After some time, but after certain delay, whatever the time you give, the delay, you apply a pi pulse after certain delay delta. What does pi pulse do? I am applying pi pulse on the x axis. You rotate along x axis like this. Then the red spin vectors move here and blue vectors move here. The red which is moving in this direction continue to move in this direction. The blue which is moving in this direction continue to move in this direction. What is happening? They start moving in the opposite directions. Which was going like this, now it will come back. One which was going like this is now starting like going like this. All the vectors give identical delay. After some time, what happens? They all come back. They were moving like this. They will again come back to x axis. You understood? All the spin vectors are brought to x axis by an antipulse. Instantaneously there is a phase coherence. And allow for some time. There is a defacing. All of them have different chemical shifts offset. As a consequence, some are moving like this, some are moving like this. They are called fast moving and slow moving components. They keep on spanning out like this, fanning out like this. After a delay delta, apply a pi pulse along x axis, rotate along x axis. Then you can see fast moving, slow moving components interchanged. They continue to move in the same direction now. What will happen? Exactly after a same amount of delay, they all overlap, come back to the same x axis. What happened? We created an echo. During this echo, what happened now? There was lots of phase differences. Chemical shifts were there. Many protons, many spins have different chemical shifts. But echo finally refocused everything, brought to the same axis. That means chemical shifts are completely refocused. Spin echoes, homonuclear case will refocus chemical shifts. Remember that. This is what is happening, and every spin vector starting on x axis will come back to the same x axis. That is what the echo. That is what I told you. The runners started from the same place, moved at different places, different times, and afterwards when they were asked to come back with the same speed, they come back to the same place. They reach the same origin. Similarly, started with the x axis, they started fanning out, again came back to the same x axis. And this is spin echo. You understood the concept of spin echo? Spin echo in the homonuclear case are refocusing the chemical shifts. This is the logic. You should remember homonuclear spin echo refocuses chemical shifts. What happens if the magnetic field is not homogeneous? All this were under the assumption magnetic field is perfectly homogeneous. But inherently there are inhomogeneities in the magnetic field. It need not be homogeneous. There will be gradients of the field. Spins experience different fields. Interestingly, they also get refocused. Field inhomogeneity is also refocused. That is the important point. Not only chemical shifts, field inhomogeneity if it is there, they are also get refocused. Why? Because their resonating frequencies are different with a different field. Again, chemical shifts will be different. Since the chemical shifts are refocused means inhomogeneities are also refocused. That is the logic. So, inhomogeneity is also refocused along with the chemical shifts. You can ask me a question. We did something in an experiment where we applied the pulse along x axis and rotated the spin vectors along the x axis like this. So, we interchange the vector directions, movement directions. What happens instead of x axis if I apply a pulse on y axis? As of course, I did not discuss all those things. In one of the previous courses, I have discussed about the pulse phase, receiver phase, everything. We can apply pulse along x axis, y axis, plus x, plus y, minus y, everything at different axes we can do. And not only 90 pulse, 180 pulse. And we can ensure This, depending upon the axis in which you apply a pulse, we can make the vectors rotate along the xy plane or in the yz plane or xz plane, either clockwise or anti-clockwise. All these things are possible. You can play with spin dynamics. So now if I apply a 180 pulse instead of 180 x pulse in the spin echo sequence, what will happen? Let us see. Consider a situation like this. I have brought all the spin vectors to x axis. Wait for some time, the fins start defacing. Wait for some more time, more spins are defacing, they are fanning out. At this stage, apply a 180 pulse. Instead of rotating along this axis, now I am applying along y axis here. So I am rotating along y axis here, not along this axis. Then what will happen? Here when I was rotating, these vectors were here, these vectors were here. But when I am rotating along this axis, this will come here, this will come here. Now remember the direction of axis on which I am rotating. Here I am rotating on the y axis, so it is like turning this thing, table, like a pancake turning. Like reversing of the pancake. This is what happens. Now wait for some time, delta, or identical time. All the spin vectors again come back. What happened here? Same. You have still refocused the chemical shifts. In the previous example, all the spin vectors were refocused along the plus x axis, but now it is refocused along minus x axis. That is all the difference. The refocusing still occurs even whether you apply a pulse along plus x axis, whether x axis or y axis, there is chemical shift refocusing. In one example, when you applied along plus x axis 180 pulse, there was a refocusing along plus x axis. If you apply 180 pulse along y axis, there was a refocusing along minus x axis. That is all. There is no difference except the refocusing axis is different, but chemical shifts are always refocused. So please remember, whether you apply a 180 pulse along x axis or 180 pulse along y axis, there is a chemical shift refocusing in the homonuclear case. Okay, this is a simple video which shows you how spin echo occurs. Look at it. It starts with here. You apply 180, come here, apply 90 pulse, bring all the spins here, they start fanning out, apply 180 pulse, it is like turning the pancake. They are rotated like this and then go there, again fanning out, and this is where we get echo. Carefully observe this. What is happening? Yeah. This 180 pulse, what it does, you see, observe. It bring the vectors here, start fanning out, and 180 pulse rotates this like this. And again, they start moving in the opposite direction. Please see the direction of rotation. The one which was rotating like this, now they continue to rotate in the same direction and then refocus. This is the video of a spin echo. Now, I also told you, if there is a magnetic field inhomogeneities, they get refocused. I will ask you a question, what happens if there are fluctuating magnetic fields? Fluctuating, not magnetic, fluctuating local fields. Of course, that is also magnetic field. The fluctuating local fields, this is not because of this inhomogeneity of the main magnetic field within the molecule. For it could be diffusion, there could be different molecular motions that can vary with time. Okay, different part of the molecule, if different molecules are there, if they take a mixture, their molecular weight could be different, they may have diffuse at different rates. Then fluctuating field, local fields will be different. If the molecules are undergoing diffusion or any other type of motion, then what will happen? Will there be a refocusing? Is the next question. They persist at different frequencies before and after 180 pulse because they are not same. Because they have precision frequency continuously keep changing because of diffusion or molecular motion. So as a consequence, they persist at different frequencies before the 180 and after the 180 pulse. There is no question of refocusing. The decay is irreversible. In other case, it is a reversible decay. That was reverse decay was there, 180 pulse brought it back. That was an echo. But here, this is not a reversible decay. The inhomogeneity, the fluctuating field because of diffusion, perfusion or molecular motions is irreversible. So they are not refocused. And because of that, you will lose the energy, lose the signal. Okay, signal will be lost. Intensity of the signal will be lost. So, this is the idea where you used to get the diffusion coefficients later. I will tell you that later when we come to that. But please remember now what is happening is, when there are field inhomogeneities, there is a refocusing. Field, local fluctuating field, because of molecular diffusion, perfusion, or different types of motion, the different precision frequencies will be there before and after 180 pulse. As a consequence, the decay is irreversible. There is no way you can refocus it. And this is what it is. This is what I just wanted to. Now we can take the example of what happens if there is a homonuclear J coupling between the two spins. This needs bit more discussion. Since the time is getting over already. What I am going to do is I will stop here. We will take the example of what happens to the spin echo when there is J coupling. Remember, so far I said there is no J coupling. I took only chemical shifts of A and X. First A was on resonance, X was moving. Then I showed both will refocus after 180 pulse. Whether you apply on X axis or Y axis, no problem. When you have number of spins, different chemical shifts, that is different offsets, they all will be fanning out different frequencies. After 180 pulse, again they will refocus. I showed that. Chemical shifts are refocused. Okay. So, and then I said this can be, in case if there is inhomogeneity, that also gets refocused. If there is a local field because of diffusion, perfusion, molecular motions, then it is a irreversible decay that cannot be refocused. So, I said homonuclear spin echo will refocus only chemical shifts. Whatever it appears as if, although there are different offsets, different chemical shift offsets, when you apply this spin echo, it appears as if there is no difference in the chemical shift among the spins. This is what is called chemical shift refocusing, which homonuclear spin echo does. But the question is, the spins are not just chemical shift alone, they could be coupled. I took a hypothetical example, there is no coupling. What happens? There is a coupling. Will it refocus? We do not know. I will explain that to you in the next class. Right now, I just wanted to tell you how spin echo works. Spin echo is just simple 90 tau 180 tau sequence. It could be 190 tau, it could be any angle. If there is any other angle, it is called an echo. First discovery of spin echo was 90 tau 90 tau 90 tau sequence. Both the delays were equal. And when it is hacked, this is called time reversal. The dephased spins will get rephased after exactly same amount of time. I gave an example of runners. Different runners will be running at different speeds. Instantaneously ask them to stop. Apply 180 pulse. Means reverse. 180 pulse is reversing. Immediately ask them to turn back. Then ask them to run now. With the same amount of time, they all come back to the same place. This is spin echo. I gave you this example. So, the spin echo refocus these things, chemical shifts, offsets. We will stop here. We will take the example of what happens with the J coupling for homonuclear, heteronuclear case, everything in the next class. Thank you very much.